So in this video we're just going to do a second worked example showing reduction of order. So we have a second order linear differential equation, x squared y double prime minus 3x y prime plus 4y, and it's equal to 0. And I'm going to give myself a little bit of space here. And then remember, we are given a solution, y sub 1 equals x squared. The general solution, which I don't need that coming up. The general solution is going to look like c sub 1 x squared plus c sub 2, and then we need another function that is a solution that's linearly independent with x squared. So because we have a second order equation, the basis for our solution space is going to have two vectors or two functions in it, and they need to be linearly independent. And what we're looking for is the second solution. And what we do, the technique that we discussed, is we guess that there's going to be some function of x, u of x, such that u times the given solution solves the differential equation. And then what we do is we take the first and the second derivative of our guess. Our guess is that the solution is going to look like u equals x squared, so we take the first and the second derivative of that, so we take y prime, and because we have a product of two functions of x, we have to use the product rule, so it's going to be u prime x squared plus 2ux, and then we need to take the second derivative of that, which will be a bit longer because we'll have two terms, each of which will require the product rule. So we'll get u prime x squared, u double prime x squared plus 2u prime x plus 2 times, and then we need the derivative of u times x, so it's going to be u prime x plus u times 1 is just u. And then we want to simplify u double prime as much as we can. I'm looking for my cheater readers. Do you see my cheater readers out there? So we'll simplify this as much as we can. U double prime x squared, yay! Now I can see, plus 2u prime x plus 2u prime x is 4u prime x. And then we get plus 2u. And then it's actually helpful to write these with the x in front, but we'll do that in the next step. So what we're going to do is take and substitute in our y double prime, our y prime, and our y. We have a y double prime, a y prime, and a y gets substituted into the equation, and it needs to equal 0. So we're going to substitute y double prime in here. So we're going to get x squared times u double prime x squared is going to be x to the 4th times u double prime plus x squared times 4u prime x is 4x cubed u prime plus x squared times 2u is going to be just 2x squared u. And then we get minus 3x times y prime. So we're going to get a minus 3. X times u prime x squared will be x cubed u prime. Minus 3 times plus 2 is minus 6. X times x is x squared, and then the u will come along for the ride. And then it'll be plus 4y times ux squared is just 4x squared u, and this is all equal to 0. And because this is a reduction of order, what has to happen is the first degree terms in here, the u's, need to cancel. If they don't cancel, you know that you've made an algebraic or differentiation error over in here, and you need to check your work on it. So right now I get 2x squared u plus 4x squared u is 6x squared u minus 6x squared u is 0. So the u to the first terms cancel. Again, if they don't cancel, you want to stop right there and check your work. And then we can simplify this. 4x cubed u prime minus 3x cubed u prime is just x cubed u prime. And we have x to the fourth u double prime plus that. And what we're shooting for is we're shooting for the form of a linear first degree differential equation that has this form. We're shooting for y prime plus p of x y equals 0 because we have a homogeneous equation here. Possibly a q of x. It would be okay if we wound up with a q of x over here. The idea is we're trying to get a reduction of order. We're trying to get from a second order differential equation and reduce it to something that's a first order differential equation, so we can use an integrating factor to integrate it. That's the goal. So to get it into this form, I'm going to need to multiply both sides by x to the negative fourth. And because I have a homogeneous equation sitting here, this is just going to be 0 on this side. X to the negative fourth times x to the fourth is 1, so I get a u double prime plus x to the negative fourth times x cubed is x to the negative first power times the u prime. And now I'm actually in this form, because what I want to recognize is that u prime is just a function and u double prime is the derivative of that function. So I could work it through from here without doing a substitution, but sometimes it helps to do a substitution to think about it. So we do w equals u prime, which means w prime is u double prime. So doing that substitution, we get w prime plus x to the negative first power times w equals 0. And in this form, it should be really clear that we have a first order linear differential equation in this form right here. And that's where the reduction of order has happened. We need to solve a second order differential equation, but we've reduced it to having to solve a first order differential equation. So I want to recognize that I have a p of x equal x to the negative first. So my integrating factor, and because I already used a u, I'm going to use a u sub 2 here. My integrating factor u sub 2 is going to equal e to the antiderivative of x to the negative first dx, which is just going to be e to the natural log of x, which is just going to be x. So my integrating factor is going to be an x. So we multiply both sides by the integrating factor. And if we've done this correctly, then x times this stuff is simply the derivative of x times w, so xw prime. And then once I get it in this form, to undo the derivative, I integrate. So we integrate xw prime dx. We integrate 0 dx. We get a constant of integration. But when we integrate 0, we get a constant, because the derivative of a constant is 0. So we get the sum of two constants here, which I'm going to name c sub 1. And the antiderivative of the derivative will give us the x times w. And now I want to multiply. I want to get the w by itself, so I multiply both sides by x inverse, which is going to give me w equals c sub, not x inverse, x to the negative first power. That was a stupid thing to say. I've been doing a lot of trig lately, and then trig, you use the inverse notation, and then it's kind of a stupid notation because it doesn't mean to the negative first power. But if you write square, tangent squared of x, it means to square it. So I think there's some funkiness going on there that I've been thinking about lately. All right, so we get w equals c sub 1 x to the negative first. I don't know why I babbled about that. I'm sorry. So w equals c sub 1 times x to the negative first, but we want to remember that w is u prime. So we really have u prime equals c sub 1 times x to the negative first. So to get u, we have to integrate u prime with respect to x, which means we have to integrate both sides. Whatever we do to one side, we do to the other. And we're going to get a second constant of integration coming out of this integration process here. And when we integrate u prime, we get u. So u is equal to c sub 1. The antiderivative of x to the negative first power, or 1 over x, is just the natural log of the absolute value of x. If we're on the interval from 0 to infinity, we don't need the absolute value symbol, so we can drop that. And then we have plus c sub 2. And then remember, our guess was that the solutions look like u equal to u times x squared. So we're guessing that y equals c sub 1 times the natural log of x plus c sub 2 times x squared, replacing u with the stuff right here. And then distributing the x squared in, we're going to get c sub 1 x times the natural log of x plus c sub 2 times x squared. And if we've done this correctly, the x squared should show up in the answer as the thing that we started with right here. Here's the x squared we started with, and there's going to be another function sitting here. And this constant could have all kinds of other constants attached to it. The idea is that this is definitely a solution to the differential equation, and this guy right here, x times the natural log of x, is linearly independent with x squared. In fact, if we calculated the Wronskian, we would discover that the Wronskian of x, ln of x, and x squared is definitely not equal to 0. I mean, we could test it by calculating the Wronskian. I think it's visually apparent that those two are linearly independent in this case. So we actually wound up with the general solution here. If I had gotten like a negative, let's suppose I had a negative and it was over 5, I want to recognize that if I plug in negative 5 for c sub 1, I would get 1 times x ln of x, and I can choose c sub 2 to be 0. And our choices of constants are arbitrary when we're doing this. The key is you want this guy here, and there's going to be some constant multiplied by it, and you can just absorb that into a single constant. So the general solution for this differential equation is going to be c sub 1 times x squared, or c sub 1 times x ln of x. It doesn't matter the order you put them in, and then c sub 2 times the other function that we came up with, x ln of x. There's your general solution. And it turns out there's a formula that you can use to directly calculate this guy right here. But in this homework assignment, I won't want us to use it. And in the subsequent video, though, we'll develop that formula.